All right, so I'm just gonna make a video here for the snow day that we missed today, which I'm gonna call for the day that I was actually sick, that we missed. So it's actually making up for that day, but we're gonna make it for today. So far we have seen that what? So we have described kinematic equations. That was the first exam, right? So we did that for both linear and uniform circular motion. We have also done now dynamics, where again, dynamics is now what actually creates the acceleration that we then use into our kinematic equations, right? So for the most part, I mean, we're basically done with the class. So I mean, that's kind of reassuring, but also kind of sad simultaneously. So the question is, why do we not end the class today if we're actually basically done with that? So what we've seen so far is that, remember, our kinematics here uses the fact that our acceleration must be equal to a constant, right? So what we've seen so far are things like inclined planes. So here's my inclined plane that I put a block on this, and then this guy has a constant acceleration down the plane, right? But what happens if we want to analyze a different system, say something more like this, which is more of a curved ramp instead? So now let's say I put a mass on here. So here's my actual mass sitting on here. And now this thing is going to move down the plane like this. Okay? So the question is, at least in the first case with the ramp here, or at least the inclined plane, this guy again has a constant acceleration. So the question is, in the second case here with the curved ramp, does this guy have a constant acceleration? Is this guy equal to a constant? Now, the quick answer is, well, no, because that's what, since this thing is not level, right? It's not a constant curve all the way through. That means at any different position, this thing is going to have an acceleration, which then depends on the position, right? So basically, it's going to depend on both the y position as well as the x position. So let me draw that actually from here. So this would be the y and the x position, which means in this case, our acceleration then is actually going to be dependent on x and y. But since X and Y are actually dependent on time, that means ultimately this guy is going to be dependent on time. Now, what that basically tells us then is that what in a situation like this, which is actually a more realistic type situation, in this case, then we can't actually use kinematics. Right? So in this case, we can't use kinematics. The kinematic equations here, since again, our acceleration is not equal to a constant. Right? So the question is, how do we actually solve a system like this? Right? Now, there's two ways we can basically do this. So one way is we can actually stop class now. Right? So this is option number one. We can stop class, and then basically I can send you guys to go learn differential equations. So have you guys learn um, differential equations, which you have to go through a couple more math classes before you actually get there. And then basically after you learn differential equations, you come back to my class. So now we can go back to Physics 205 and then actually learn how to do this by solving a differential equation. Now, that's not exactly practical, and that's not the way that the class is actually set up. So basically what we have to do then is our second alternative, which is now find an alternative way of determining the motion of the object. Because ultimately, this is what we want. So again, what we want to do is we want to predict where this object is going to be at any given moment of time. So what we really want to do then is what? Determine what this thing is actually doing. Now, we have to do that in an alternative way because we need to find a way that doesn't depend on kinematics or the acceleration. So basically, we want to find a way to do this without direct reference to the kinematic equations, nor Newton's laws. So basically what we're going to do at the stage is basically find an alternative way that blends the two things that we've done together. So basically we want to blend the kinematic equations with Newton's laws to then come up with an alternative way of actually doing the same thing without actually having to refer directly to the kinematic equations or Newton's laws. And so we want to find a more general way of actually being able to do this. Now, to do this, we're going to get a little abstract for a little while, but we'll bring it all back together and then it'll hopefully make a whole bunch of sense in this case. Okay. So basically, our story then is going to start with this idea called work. Okay. So what is work? So work we're going to call W. And basically in physics, what this does then is, let's say I have a constant force. Okay, so my force in this case is equal to a constant. So I'm applying a constant force to some sort of object. And we want to say how much work did I actually do on the object by moving my object from one position here, right? So let's say this is my initial position to some final position here, where this guy undergoes some sort of displacement. Okay, so this is my displacement. In this case, my displacement, of course, is going to be to the right. So this is my displacement written as a vector. So let's say we're pushing on this with some sort of force. My force is up in this type of direction here. So we then define the work then as equal to the magnitude of the force times then the magnitude of the displacement times cosine of the angle between the two. Now, let's talk a little bit about what this thing actually means. So again, my displacement is in this direction. Right? So what is this thing saying? So this thing is saying is that if these are at an angle of theta, then what happens then is what? The only way to do work on the system is if somehow the force acting on my object here is somehow parallel to the object of the or parallel to the motion of the object, right? So that's basically what this two terms here are basically saying. So what this says then is I want the parallel component of the force. So again, we can always break down my force into this component here, which is my F cosine of theta, due to the fact that this is my adjacent side, which is going to be my parallel portion of the force. Okay? So ultimately, what does this tell me? So this tells me that work is going to depend on multiple things. So first of all, what does work depend on? So it first depends on the fact that my force cannot be equal to zero. Okay? So if my force is equal to zero, then that means I do no work, right? So if my force is equal to zero, then my work then is going to be equal to zero. Second thing is it depends on the angle. So if my angle, for example, is 90 degrees or pi over 2 radians, that means then in this case, I'm going to do no work. So meaning if I kind of redraw my picture here, so here's my mass, and if I'm applying my force down in this direction, so this is my force, but my displacement then in this case is going to be in this direction. Let's say it's moving this way. In this case, since it's a 90-degree angle, that means that what? No work is done because here my force is perpendicular to the direction of the motion, but the only way to get a work done is if it's parallel to the direction of motion. So again, it's only the parallel component of the force. But here, since there's no parallel component, that means then my work then is equal to zero. So what this means then is what? If I was standing here, right, or walking across the room and I'm carrying a bucket, right? So say here's my bucket. So my displacement in this case is going to be in this direction, but I'm applying a force upward in this direction. That means in this case, I do no work. My work then is simply equal to zero. So again, if my force is, again, perpendicular to the direction at which it is that it's moving, then I do no work. The third thing we can notice from this then is what? If my displacement is equal to zero, then again, my work is going to be equal to zero, right? So what this means then is if I had a wall and then I'm pushing against the wall, so here I am pushing against the wall, so I'm going to supply a force in this direction. So this is the force from me on the wall, or the force on the wall by me. So in this case, since there's no displacement, then that means my work then I'm applying to this guy is simply equal to zero. So we have to be a little bit careful when it comes to things like terminology, when it comes to our everyday understanding of work versus that of physics. So in physics, again, all that means is what? I have to have these three things. So there has to be a non-zero force. There has to be a perpendicular or parallel portion of the force, meaning if my force applied is perpendicular to the direction of the motion, I do no work. And I have to actually move the object, which means I do work. If I don't move the object, then I do no work in this case, because here my displacement then is simply equal to 0, right? Now, this is opposite to what we call work in reality, or at least in the usual everyday English language, because here we simply say that work is what we get paid for effectively, right? Or at least what I have to do outside of school, like homework or things like that, right? So in this case, none of those things, at least in most cases, don't actually correspond to what we define as work in physics terminology, because typically if I'm getting paid to sit at a desk and simply type keys all day, I'm not doing any work according to physics, right? Or if I carry some heavy object, well, let's say I start off here carrying some object, and then I go out this distance of, say, X initial, and then I come back to the same distance so that I'm at the same location at the end of the day, then in this case, my displacement, of course, is going to be equal to 0, which means I'm going to do no work. So in this case, absolutely no work. So again, just sitting home doing my homework. I hit a wrong button here. So basically just sitting here doing my homework, I'm not getting paid for that at the end of the day, according to physics, because I've done no work, right? Or if I sit there and I'm holding against the wall and I say I'm holding up the wall the entire day, and I go to my boss at the end of the day and say, okay, I've held up the wall the entire day, I get paid. He's going to say no, because according to physics, you did no actual work, right? So we just have to be a little bit careful when it comes to terminology. So work in physics is very specific. Again, it's equal to this guy here, so I'll rewrite it down. So again, in physics, work is equal to the force times displacement times cosine of the angle between the two. Now, let's make a couple observations about this guy real quick. So observations before we move on. So observation number 1 is that, let's look at the units of work. So the units of work are going to be the same thing as a Newton times a meter. And this thing gets a special name. This is what we call a capital J, which is what's called a joule. So the units of work are Newton times a meter, which is the same thing as a kilogram meter squared per second squared, which is what we call a joule. And again, this thing has units of joules. Observation number 2 is that the work is going to be dependent on who it is that I'm actually talking about. So work is dependent on the force, or alternatively, on perspective. So what do I mean by that? What I mean by that is, let's say I'm standing here. Right, sorry, my camera doesn't work on my desktop. But anyways, let's say I start off and I take an object from the ground. Right, so let's say here's my object, and I'm going to move it from the ground up to this location here, which means my displacement is this way. Okay. Now, in this case, what this means is I'm applying an upward force onto this guy, but simultaneously we have gravity. So my gravitational force is going to be acting downward. So this is my mg. Now, if I ask the question, how much work did I do? So the work done by me then is going to be equal to the force times the displacement times cosine of the angle between the two. But in this case, since my displacement is upward, my force is upward, then that means these two guys are parallel. So again, in this case, my force is this way. My displacement is also this way, which means that the angle between the two of these guys is simply equal to 0. So in this case, I'm going to do a work of simply F times delta X. Okay. Now, simultaneously, we can then ask, what is the work done by gravity? Well, the work done by gravity then is going to be the gravitational force, right, times then the displacement, times then cosine of the angle between them. Now, in this case, since my gravitational force is a downward, right, pointing in this direction, mg, and then my displacement is upward in this direction, so this is my displacement, then the angle between these two guys is theta, which is equal to 180 degrees, or pi radians. Okay. So plugging that in, I'm going to get then that this is going to be equal to the weight times delta x times then cosine of 180 degrees. But cosine of 180 degrees is simply -1, so it's going to be minus fg delta x. Okay. So that means that when I lift this object, let's say it's a chair, I'm doing positive work while the gravitational force is doing negative work. Okay. Now, in the opposite case, let's say I'm now standing here, And I now take the same object, but I'm going to lower it now. So I'm still applying the force upward of F. Gravitational force still acts straight down. But now in this case, I'm going to lower it. So now I'm going to move it from this location back to the floor. Okay. Now in this scenario, of course, it's just going to switch. Okay. So now the work done by me is going to be equal to the force I'm applying times delta x times cosine of the angle between the two. But since my force is upward, the displacement is downward, then that means that what? The angle between the two of these guys is, again, theta equal to 180 degrees. So this is going to be f times delta x times cosine of equal to 180, which is then equal to what? Negative the force by me times delta x. So when I lower it, I'm doing a negative work because in this case, my force is in the opposite direction of that of the displacement. But simultaneously, the work done by gravity is then going to be equal to the gravitational force times then the displacement times cosine of the angle between the two. But again, in this case, my displacement is downward. My gravitational force is also downward, which means the angle between the two of these guys is simply going to be 0. Right? So in this case, theta is equal to 0, which means this is going to be just f of g times delta x times cosine of 0, but cosine of 0 is 1. So in this case, the gravitational force is doing positive work in this particular scenario. So this basically brings me to observation number 3, which is that work can be positive or it can be negative. Right? So work can be positive or work can be negative. Now, the last observation we can make is number 4 in the fact that work, since this guy's equal to, again, let me write it this way, the magnitude of the force times the magnitude of the angle times cosine angle between the two. Since I'm dealing with the magnitudes of each one of these guys, then this means that work is actually a scalar quantity. So unlike a force or displacement by its nature, which are vectorial quantities, this guy is actually a scalar quantity. So this is a new way to multiply vectors together. So notice what's happening here is I'm actually taking a vector, which is force, and multiplying by another vector, which is displacement, to then get a scalar quantity out of it. All right, so even though I'm taking two vectors and multiplying them together, we're getting actually a scalar quantity. So this brings up the second way of multiplying vectors. So back in the day, when we were talking about vectors in general, what we said was that there are 3 ways to multiply a vector. So let's do it this way. Ways to multiply vectors. So the first case was what? Multiplying by a scalar. We talked at length about what that did. So this is the second way, which is when we take two vectors, multiply them, and we actually get a scalar. So this is what's known as the scalar or dot product. Okay. So this is our second way to actually multiply vectors together. So let's talk about scalar products or dot products here for a little bit, because this is going to be kind of important. So let's talk about our scalar / dot products. Good. So let's talk about these things. So first of all, let's say that I have two vectors. So I have vector A, which is equal to AX in the I hat direction, plus AY in the J hat direction, plus AZ in the K hat direction. I also have some vector B, which is then equal to BX in the I hat direction, plus then BY in the J hat direction, plus BZ in the K hat direction. Okay, from here we can define our scalar product or our dot product, which we write as A dotted by B. So notice here, this thing specifically has a dot. This is not the same thing as A cross B. So this is something different. So these two things are not the same. And we'll see that later when we get to things like torque. So this guy here is going to become important when it comes to torque. Okay, so we'll get to torque later. I'm not going to spoil what torque is now. But anyways, so this is what we call a dot product. So notice again, when we write it out, we're writing it with a dot in between the two. So let's talk about what this thing actually does. So what's a dot product? So the way the dot product works is we get A dotted with B. So what does this mean? So this means we're going to take our vector AX in the I hat direction plus AY in the J hat direction plus AZ in the K hat direction, dotted then with BX in the I hat plus BY in the J hat plus BZ in the K hat direction. Now, let's write all this out. So this is going to become what? AX times BX times I hat dotted with I hats plus AY times BX times J hat dotted with I hat plus AZ times BX times K hat dotted with I hat, plus all the other cross terms, right? So I'm going to get a AXBY with an I hat dotted with J hat, plus then a AY times BY times J dotted with J. And then we're going to get a plus, what's that, AZ times BY with a K hat dotted with a J hat. One more line, so plus AX times BZ. And then we get an I hat dotted with K hat plus AY times BZ. And then we get a J hat dotted with a K hat. And then plus, finally, AZ times BZ with a K hat dotted with a K hat. Now, first of all, let's talk about some things here. So first of all, what does a dot product actually mean? So what is the meaning of a dot product? So as we saw from the definition of work, work is equal to, again, the magnitude of the force times the magnitude of the displacement times cosine of angle between the two. So this means actually an alternative way of writing this guy, A dot B, by following this means that this is going to be the magnitude of A times the magnitude of B times cosine and angle between the two. Now, I'll go back to that other definition in just a second. Now, what does this say? So what this thing says then is, again, if my angle is equal to 90 degrees, then my dot product is simply equal to 0. When my angle is equal to, let me do this in a different color, 0 degrees, this means that this guy is simply equal to the magnitude of A times the magnitude of B. Okay? So what this thing says then is that what? The dot product is maximum, right? Because this is the biggest value I'm going to get, because when I multiply by cosine of any other number, it's going to be less than 1. So this tells me that it's maximum when the two are parallel to each other. So basically, what this thing is telling me then is that what? The dot product tells me how parallel two vectors are to each other. Now, why this is important is when we go back to our ij's and k's here. So remember, if I have my coordinate system, let's say this is x, this is y, and this is z, then we know I hat, j hat, and k hat are the unit vectors which point in these different directions. Now, what I know then is by definition, I is perpendicular to j, which is then perpendicular to k. So all of these are mutually perpendicular to each other. So what this basically tells me then is that terms that go as I dot j, which is then equal to I dot k, which is then equal to what? Let's say here, j dot k are all going to be equal to 0 because the dot product tells me how parallel these things are. And by definition, all the unit vectors are perpendicular. So in all of these cases, the angle is simply equal to 90 degrees, which means all these dot products then are going to be equal to 0. So the only way my dot products are not equal to 0 is when I have I dotted with I, which is then equal then to what? J dotted with J, which is then equal to K dotted with K, which is simply equal to 1. And the reason for that is, remember that we're dealing with unit vectors, which means that the magnitude of the unit vector is simply equal to 1. So in this case, that means that I dotted with I is the same thing as 1 times cosine of 0, There we go, which is equal to 1. So in this case, I get a 1 times a 1 times a 1, which is simply equal to 1. Now, going back to our previous, what that means then is anything that has anything other than a I dotted with an I, a J dotted with a J, or a K dotted with a J is by then default 0, right? So that means this term is going to be 0, this term is going to be 0, this term is going to be 0, this term would be 0, this term would be 0, and finally this term would be 0. So in this case, then, we can then say that's what? Our A dotted with B is then going to be the same thing then as AX times BX times I dotted with I plus AY times BY times J dotted with J plus AZ times BZ all dotted or all times K hat dotted with K hat. But again, these guys are simply 1. So what this says then is finally, in component form, this becomes AXBX plus AY times BY plus AZ times BZ. So putting everything together, what this says then is that we have two alternative definitions of our dot product. So we have A dotted with B is then equal to AXBX plus AYBY plus AZ times BZ, which is also equal to the magnitude of A times the magnitude of B times then cosine of the angle between the two. Okay. Now, other things to talk about this. So first of all, it doesn't matter the order in which I do the dot products. So what this means then is that B dotted with A is exactly equal to A dotted with B. And the reason for that is, again, we can just go back to these definitions here. So if I switch A and B, that means these two terms just switch, but I get the same thing. And then same thing here, these guys just simply switch, which means that these guys commute, right? So this satisfies our commutative property. The other thing to point out here is that if vector A, say, pointed off in this direction, and then vector B points off in this direction, so that this is the angle between the two, the way this works is, at least the geometrical interpretation, is I would drop a perpendicular from A onto B, and then this distance here is actually equal to A dot B. So what this is telling me then is that the amount of A that lies along the direction of B, or differently, what that means is how much of A is parallel to the direction of B. Now, if I do the same thing in the other direction, so I drop a perpendicular down here, then this distance here is then B dotted with A. But in this case, it's the same exact thing. So again, these two are the same distance overall. So again, all the dot product tells me then is how parallel is one vector to another vector, right? So this is our geometrical interpretation. So our geometrical interpretation is how much of A lies along the direction of B. Or how much of B lies along the direction of A. But again, it simply means how parallel are two vectors to each other. So how parallel are two vectors. Okay. So this is what we call a dot product. So let's do a couple examples to kind of get used to this a little bit. So notice another thing that this definition tells me then is I can always determine the angle between two vectors if I know the vectors in component form. Right, so as long as I know these vectors in component form, I can then determine the angle between these two vectors. And that's the first example we're going to look at. So let's look at an example. So this example says that we have two vectors, vector A, which is equal to 3 in the I hat direction, plus 3 in the J hat direction, plus 3 in the K hat direction. And then I have my vector B, which is then equal to 2 in the I hat, plus 1 in the J hat, plus 3 in the K hat direction. Okay. What we want to know in this case then is what is the angle between these two vectors? All right, so first things first, let's draw these vectors. Okay, so draw that a little bit nicer. Still can't draw a straight line, but that's okay. So let's say this is, again, is my X direction, Y direction, and then Z direction. Okay, so for vector A, we would then go, what, 3 units along the X direction, 3 units along the Y direction, So that's going to create this point here. Okay. And then we're going to go up by 3 units in the z direction. So that is going to give me this point here, right, when I come up like this, which means that this is my vector A. Okay, so my vector A is pointing off in this direction. It's projected into the XY plane. Simultaneously, for the B, I'm going to go 2 units in the X direction, 1 unit then in the Y direction. So it's going to give me this point. And again, 3 units up in the Z direction. So that's going to be what? Here, if I follow a straight line from there, which means then my B is going to point this way. Okay. So what I want to know is, what is this angle here? What is the angle theta between these two vectors? Okay. So let's do that. So first things first, let's look at the dot product itself. So using the fact that we're going to do it in component form. So in component form, this is going to be the same thing then as x hat, or sorry, ax times bx plus ay times by plus az times bz. So plug in my numbers. What I'm going to get then is what, a 2, let's do it this way, 3 times 2 plus 3 times 1 plus 3 times 3. So it's going to be the same thing then as what, 6 plus 3 plus 9, which is the same thing as 18, right? So this is my dot product in component form. Now, alternatively, we know that the other definition is A dotted with B is then equal to the magnitude of A times the magnitude of B times cosine of the angle between the two. Okay? Now, from this, what we can then say is what? If I solve this for the angle, I would divide both sides by the magnitude of A and the magnitude of B, and then take an arc cosine. So my angle between the two will then be the arc cosine of the components. So I'm going to get A x bx plus then a y by plus then a z bz divided by the magnitude of A times the magnitude of B. And that's going to be equal to the angle between the two. So we've already done the first part, so let's go ahead and find the magnitude of A and the magnitude of B. So the magnitude of A is just going to be the square root of, by Pythagorean's theorem, 3 squared plus 3 squared plus 3 squared, which is the same thing as 3 times the square roots of 3. That's okay? Hopefully? Good. So, because again, if I factor out the 3, that gives me a 3 out front, and then I have a 1 plus 1 plus 1, which is the 3. So let's look at the magnitude of B. So it's going to be the square root of, by Pythagorean's theorem, 2 squared plus 1 squared plus 3 squared. So it's going to be the same thing then as what? The square root of 4 plus 1 plus 9. So it's the same thing as the square root of 14. Now, putting everything together, what this says then is that my angle is going to be the inverse or arc cosine of 18 divided by 3 square root of 3 times the square root of 14. Plugging in my numbers, putting my calculator, what I get in this case then is that they're at a 22.21 degree angle between the two of them. So my angle between the two is 22.21 degrees. So let's do another one. So this one, we're actually going to use more the dot products, and let's draw a picture here. So let's say this is my coordinate system. So I'm only going to do a 2-dimensional in this case. Let's say this is X and this is Y. And we're going to define 3 vectors this way. So A is going to point this direction. So it's my vector A. B is going to point up this way at a 90-degree angle. So this is my B. And then C, you see in yellow here, is going to be the hypotenuse of this triangle pointing back to the direction of A. So this is my vector of C. Okay, now what we also know, or at least what we're told in the problem here, is that the magnitude of A is equal to 4. So it's 4 units long, whatever that is. Magnitude of B is simply equal then to 3. Okay, and then C has a magnitude of 5. That's a 3, 4, 5 triangle. So from here, what we want to determine then is multiple things. So part A, we want to know what is the dot product between A and B. Part B, we want to know what is the dot product between A and C. And then finally, for part C, we want to know what is the dot product between B and C. All right. So first things first, since we know these guys in the picture form, and we know this is my I hat direction and this is my J hat direction. So let's write each one of these vectors in component form. So here I'm going to get A then is equal to the magnitude of A, which in this case is 4, in the I hat direction. For B, only points in the J hat direction, so it's going to be 3 in the J hat direction. And then finally C, it's going to be pointing what? In the negative A direction, so that's going to be minus 4 I hats, and then it's in the negative B direction, so I'm going to get a minus 3 J hats. Okay, so good. So let's look at part A first. So part A then, we want to know what is A dotted with B. Okay, so in this case, this is going to be what? 4 I hats dotted with 3 J hats, which is the same thing as 12 times I dot J. But I dot J, as we already said, is simply equal to 0. So at the end of the day, this is going to be 0. Good. So next up, let's do part B. So part B, we're now going to do A dotted with C. So it's going to be the same thing then as 4 I hat dotted with minus 4 I hats minus 3 J hats. So let's write that down. So I'm going to get a minus 16 I hat dotted with I hats minus 12 I hat dotted with J hats. But again, we know I hat dotted with J hat is simply 0. We also know that I hat dotted with I hat is 1. So this guy's going to become equal to simply negative 16. And then finally, let's look at B dotted with C. So B dotted with C for part C is then equal to what? So this is 3 J hat dotted with minus 4 I hat minus 3 J hats. So this is going to be minus 12 times J hat dotted with I hat minus 9 J hat dotted with J hat. Now again, we know, again, J hat dotted with I hat is 0 because they are perpendicular to each other by definition. And then this guy's going to be 1. So this is going to be equal to simply minus 9. So this is the dot product. So again, the main important thing about a dot product is to note that what? It tells me how parallel two vectors are to each other. So if I have two vectors which are perpendicular to each other, then the dot product is simply going to be 0 because there's nothing that's parallel. So these guys just have to be equal to 0. Okay. So good. So this means that now using our dot product, our dot or a scalar product, we can now rewrite then the work. So again, we said work was equal to the magnitude of the force times the magnitude of the displacement times cosine of the angle between the two, or in terms of a dot product, this is going to be force dotted by the displacement. Now, in most cases, we can take our displacement is equal to, as we know, the final position minus the initial position. But we can always set our initial position equal to 0. So this is going to be just simply equal to the final position. So in most cases, we're going to write this simply as the force dotted by the final position. So cool. So this is our definition of work. So again, work can be positive or negative, and it can be, and it's a scalar quantity. So good. So let's look at an example using the work. So let's say that we have a worker pushes a sled with a force of 40 newtons. Okay, so here's my sled. My sled is going to have some mass to it, right? So this guy's going to have a mass. We're going to start off here and we're going to push this guy some distance, delta x, which is then equal to 6 meters. Okay, so in this case, he's going to push parallel to the ground. So the force he's applying is in this direction. So this is F, where the magnitude of F is simply equal to what I say was 40 newtons. And we're going to have a friction force acting on it back in this direction, which is going to be kinetic friction, where the magnitude of the kinetic friction is equal to 24 newtons. So good. So in this case, it wants to know what then is the network. So we want to know what is the network acting on the system. So what is my network? So good. So what do we know? So we know that work, again, is force times distance times cosine of the angle between the two, which means net work then is going to be the net force times the displacement times cosine of the angle between the two, where the net force is the same thing as the sum of the forces. So it's going to be the sum of the forces. In this case, it's only moving in the x direction, so we care about the sum of the forces in the x direction times the displacement times cosine of the angle between the two. Now, in this case, since we have the force to the right, the friction to the left, that means the net force, so the sum of the forces, then is going to be equal to just the red arrow here. So it's going to be my sum of my forces, right? So good. So my sum of my forces then, according to my picture, ooh, that went away. There we go. Is then going to be equal then simply to what? The force minus then the friction force, because that's the net force, times my displacement times cosine of the angle between the two. Now, in this case, since my displacement is to the right, my force, or my net force in this case, is also equal or pointing to the right. That means the angle between the two in this case is going to be 0 degrees. So here, this is going to be the same thing then as what? Just simply the force minus the friction force times my displacement. So number-wise, this is going to be the same thing as 40 minus 24 all times 6. Right? So plugging my numbers, what I get in this case then is this is going to be 96 joules. It's okay. Now, an alternative way to do this, and what we can actually see from here is, let's write this out a little bit further. Okay? So let's do that. So in this case, I can look at my net work, which is equal to, again, my net force times my displacement times cosine of the angle between the two, which here is going to be the same thing then as the force minus the friction force times then my displacement times cosine of the angle. Now, let's write all this out. So let's kind of FOIL all this out. So here I'm going to get my force times my displacement times cosine of the angle between the two, minus then my force times then my displacement times cosine of the angle between the two. Okay. Now, what have we just done here? So basically what I've done is now written this as two different work terms. Right? And the easiest way to see that is, again, let's go back to our picture. So we know in this case, our force is pointing in the same direction as the displacement, which means the angle between the two of those is simply 0, right? So it's going to be the same thing then as the force times the displacement times cosine of 0, which is the same thing as the force times the displacement, okay? For the other parts, we know the friction force is in the backwards direction. We know the displacement, again, is in the forward direction, which means the angle between the two of those is going to be 180 degrees. So in this case, we can rewrite this then as plus f sub k times my displacement times then cosine of 180 degrees, right? Good. Now, actually, let me get rid of this term. So notice that my first term here is nothing more than the work done by the force. And then my second term here is the work done by the friction force. So an alternative way to do this is to say that the net work is simply then equal to the work done by the force plus the work done by the friction force. Or in a more general statement, what this means then is that the net work then is going to be equal to the work done by all the individual forces. So this is an alternative way of doing the same thing. So all this says then is that the net work is then equal to the sum over all the individual works. So it's an alternative way of doing the same thing. So next up, let's do another example. So here, let's say, again, I'm going to have some sled here. So here's my sled. We're going to have some mass. My mass in this case is going to be 50 kilograms. And we're going to pull on this with a rope, and we're going to pull it over some displacement. So this is going to be my delta x, which is equal to 5 meters. And we're going to pull on this in one of two ways. So in part A, oops, sorry, there's also a coefficient of friction here. So this has a coefficient of kinetic friction, which is 0.1. So in the first case, we're going to pull on it where the force is going to be applied in this direction. So this is part A, where this force has a magnitude of 120 newtons. And then in part B, we're going to pull it up at some angle here. So this is the direction of my force for part B, which is at an angle of theta, where theta in this case is going to be, what, 30 degrees. Okay. So again, what I want to know is, what is my net work? Okay. So let's do this the second way this time. So let's say that in this case, my net work then is going to be equal to what? The work done by the force plus the work done by the normal force plus the work done by the gravitational force plus then the work done by friction. Okay. Because in this case, what we know is what? We have our normal force acting on this guy, where my normal force then is going to point in this direction, right? It's my normal force. There's also a weight acting on here, so I get mg down in this direction. Now, also pay attention to the fact that since my displacement in this case, so let me draw my displacement on here, is going to be to the right, then that means that the angle between my displacement and the gravitational force is 90 degrees, and the angle between my normal force and my displacement is also 90 degrees, which means that those two are simply going to give me zero work. And so this guy's going to boil down then to the work done by the force plus then the work done by the friction. So good. So in the first case, this is going to be then equal to the force times the displacement times cosine of the angle between the two. But since the force is in the same direction as the displacement, this is going to be at 0 degrees. Plus then the work done by the friction. So that's going to be my frictional force times my displacement times cosine of the angle between the two. But my friction force is acting in the opposite direction as the displacement. So this angle here is going to be 180 degrees. So I'm going to get a cosine of 180 degrees. Okay. So in this case, this is going to be the same thing as F times my displacement minus my friction force times my displacement. Now here, since I have a flat horizontal surface, my normal force then is going to be simply equal to the weight, and we know our friction force is equal to the coefficient times the weight. Okay. So in this case, this is going to become finally the force minus then the coefficient times mg, all times my displacement. So when it's parallel to the ground, this gives me a net work of 355 joules. Now in the second case, let's do the same thing. So here, for the second case, part B, we get the net work then is equal to the work of the force plus the work done by the gravitational force plus the work done by the normal force plus then the work done by friction. Now again, the gravitational force and the normal force are perpendicular to the direction. And so those guys are going to give me 0 work. So again, this is going to be the work done by the friction plus the work done by the pulling force. So this is by, again, definition, the force times the displacement times cosine of the angle between the two. Now, in this case, my displacement, again, is to the right, but now my force is at this angle here. That means I only care about the cosine portion of this guy. So it's going to be cosine of 30 degrees. Plus my then friction force times then the displacement times cosine of the angle between those, but same just like last time, my friction force is always opposite the direction of the displacement. So I'm going to get a cosine of 180 degrees. So this guy's going to be equal then to the force times the displacement times cosine of 30 degrees minus my friction force times my displacement. Now in this case, what do we know? We know in the y direction, we're going to have my normal force pushing upward. Let's draw that guy here. Got our normal force this way. We have our weight down in this direction, but then we also have the applied force in, this direction. So that means if I look at the sum of my forces in my y direction, so in the y direction, we have the sum of the forces in the y are then equal to 0. So I get my normal force plus my f sine of theta minus mg then is equal to 0, which means our normal force in this case is going to be mg minus f sine of theta. Okay. So plugging that in here, so this guy's going to become equal to f cosine of theta minus mu sub k mg minus f sine of theta, which in this case again is 30 degrees. I'll just leave it that way. All times my displacement delta x. So this is going to be then equal to 304.6 joules. So in this case, it's less work done by pulling it at an angle of theta versus that of pulling it at an angle of 0 degrees. And the reason for that is, again, in the first case, we're putting all the force then into the horizontal direction, which means that all of the force, 120 newtons, is in the same direction. However, the horizontal, right, in the second case, it's only the horizontal component, which means there's less force in the horizontal direction, which is why we have less force. So let's make one more observation before we move on. And our last observation is that notice that work gives no notion of time. So no notion of time. Okay. So what does that mean? So what that means is, again, let's say I start off with my object here and I apply some force here, F, and I move my displacement here. But let's say this takes me 10 seconds versus the same force with the same amount of distance, but it takes me 1 second. Right? Now, as far as each one of these scenarios is concerned, the work done for 10 seconds versus work done by 1 second is exactly the same. And they're the same because the displacement is the same, the force is the same, and then by our definition of work, which is simply force times displacement times cosine of the angle between the two, they do exactly the same amount of work. So there is zero notion of time in this particular case. So it doesn't matter basically how much time it takes, the amount of work done is exactly the same. So whether I do it in 10 seconds or if I do it in 1 second, they are the same. Now, what does change is something we'll come to at the end of this chapter, which is called power. So power will be different, but the work is the same. So again, there's no notion of time when it comes to work. All right, so I think I've probably gone over my 50 minutes at this stage, which means that tomorrow we'll start off with what's known as kinetic energy. So we'll start talking about kinetic energy, and then we'll talk about the relationship between kinetic energy and work. But we'll do that tomorrow. Okay. So that's it. Make sure you watch this before you come into class, because we're going to start off with kinetic energy and move on from there. So if you don't know what we're talking about, then that won't be helpful. All right. So I'll hopefully see everybody tomorrow, if we're not canceled again tomorrow, which I don't think we should be because it hasn't snowed in a long time. But anyways, all right. I will see everybody tomorrow.